Welcome back to my YouTube channel. In our previous video of Form 4 Chapter 4 Physics for Heat is Heat, which is our first part. In first part of our video, I've shown you thermoequilibrium. So if you're unaware of it, you're watching it and you haven't watched my part 1, then you should go back to my previous video from my blog or from my YouTube channel and look for this title of thermoequilibrium from Physics Form 4 Chapter 4 thermoequilibrium, where thermoequilibrium is actually called the zero law of thermodynamics. It means it defines as there's no net flow of heat. Temperature of the two objects are equal. No net flow doesn't mean that the heat doesn't flow. No net flow meaning the amount of heat go to the left, it will be the same as the amount of heat go to the right, or up and down, so that the both temperature is the same. And also in our previous video, I showed you on how to calibrate a thermometer is by making use of the freezing point and boiling point of water. So first of all, you get the ice, which is freezing point, put in your thermometer with unknown scale. Find out where's the lowest point. It takes some time for heat to exchange. For heat exchange, you take time. So the length is the base length for 0 degree, and then you use the same thermometer, test the boiling point. Then you get one length. Then the boiling point length you subtract with the freezing point length. The changes of length represents 100 degree. So if you know that length and you know it's 100 degree, so if you're given an unknown length, all you need to do is you convert them. Say if 100 degrees is 30, let's say 100 degree is actually equal to 25 cm. So if your unknown length is says 10 centimeter, so all you need to do, the temperature would be 10 over 25 times 4. So it's about 40 degree. Okay, so that's how you calibrate the thermometer, and also types of thermometer and the material used for thermometer, the characteristic. Okay, because they will expand linearly, right? Because they possess thermometric property. Okay, and then the last part of my previous video is specific heat capacity, where over here I've shown you on a concept where the heat, your heated object, is related to the kinetic energy of the atom binding within the material. So meaning, if the temperature of the material is a degree of hotness, if the temperature of the material increases drastically, meaning the molecule of the material vibrates a lot, the kinetic energy is high, which also tells that the bonding is weak. If the bonding is weak, then it will vibrate easily. If the bonding between atom and atom is strong, then it won't vibrate so much. Okay, it's an analogy. Then specific heat by definition. What's specific heat? Specific heat is amount of energy measured in joule, amount of energy required to increase 1 kg per kg, 1 kg per 1 degree C. So that's the definition. Okay, so this is what we have gone through in the past, and from this equation, from here, this unit, you were able to get an equation where the energy Q is equals to mc theta. Okay, so this is the next part actually. Okay, from specific heat, it's not actually an equation. It's from the definition, and then you come to have this symbol and get this so-called equation. Is that the amount of energy is mass in kg times specific heat of the material times the increase of temperature, the increase or decrease of temperature, you call the changes of temperature. Now, this is what you call the law of, this is where leads us to today's video, where I would call it as the law of conservation of energy. Conserve, meaning you cannot destroy it. Conservation of energy. meaning energy cannot be destroyed or created, but it can be transformed from one form to another. Okay, so this is where it leads to. Okay, and this is also later on you learn is called the first law of thermodynamics. Thermodynamic. Okay, first law of thermodynamics. Zero law of thermodynamics is the thermal equilibrium. First law is the conservation law of energy. So what do you learn here? The same equation you will learn here is that energy can be transferred from one form to another, meaning it can be transformed from electric to kinetic, and kinetic to heat. Okay, so one equation is a quite general equation, is kinetic energy half mv squared. You have gone through my Form 4 video. Kinetic energy can be transformed to kinetic interrelated to mc theta, to heat energy, which is mc theta. Okay, kinetic to heat, heat to kinetic, kinetic to heat, heat to kinetic. So this is what happened to a moving object. It's transformed into heat energy when it's brought to rest by frictional force. Okay, the same is true potential energy of falling. Okay, let's say you have high water in the high stream, go to downstream, the temperature difference could be as high as 2 degrees C. So you have kinetic energy, you have gravitational potential energy, mgh, mass, gravity, height, meter, interchangeable, can be transformed from one to another to heat. Whenever there's a change in temperature increase, then it's mc theta straight away. This is what you need to use. Okay. Besides that, electrical energy. These days you have electric kettle, isn't it? So Q is PT, power, time is equals to the temperature increase, isn't it? The water boils. Okay, theta equals to mc theta. 3 equation. Okay, and the power unit is in watt. Okay, in watt. Okay, W-A-T-T, watt. Okay, so all you need to do is go through your textbook, read through the setup of experiment. The arrangement of apparatus is important because you need it in your paper 3. When you read on your reference textbook, look for the arrangement of apparatus. Look at it carefully. Where is the thermometer? Where is the power source? Where is the heater? And also a stirrer. Don't forget, okay, in this chapter especially, polystyrene sheet. Polystyrene sheet is meant to, is a heat insulator. And felt cloth, the same with felt cloth, so that you can wind around the beaker to prevent heat loss. Okay, and then example for the last one, I think is a good example. Electrical energy to heat. So you should view this, and this video is a guide for you. It's not meant to replace a reference, so you need your reference book. Okay, your reference in some of books you have a beaker, okay, insulated by polystyrene sheets, okay, and then wool cloth, because you can't wind around polystyrene cloth over beaker, so you use a tissue paper or felt cloth. Okay, it could be felt cloth or wool. Okay, here this is the polystyrene. It's a heat insulator. Okay. So what you have, the key features, one would be a thermometer, a famous thermometer. Okay, then don't forget your heater. I have one video real-time video. I mean a real video to have to guide you on how to dismantle your home kettle, but because it's leakage, so it's leaked. So what happened is I have a video of that. Okay, I'm in a stirrer. Okay, and then water surrounding it. So what happened is maybe a plus and minus, minus and plus. What happened here is electric current V goes in and out, in and out. What happened? The coiling here will heat up because of resistance. Will heat up the water, and then the water, what happened? Absorb the heat. So the kinetic energy increases and transform into heat, and then they pick up by the thermometer. Okay, you read from your reference text for detail how the experiment to be set up. You need your reference, you need your textbook. Okay, so in this kind of experiment, it's only one thing. There's no other equation. There's only one equation. Electricity, so it's PT. P is power, T is time. Is equals to mc theta. That's all. Okay. Normally, maybe this is what, 50 watt, isn't it? So this is yeah. Okay. So we're not going to give you some calculation because calculation do it sometimes. Now it's all about concept. Okay. It's in watt. So from here, how can you determine? Okay, you want to find out what's the specific heat capacity for this liquid. Maybe it's oil or unknown water, unknown liquid. It's not water, it's liquid. Yeah? Not necessarily to be water, it's liquid. So how are we going to find out this easily? You set this experiment, set up. Yeah. Then what you do is from here get the information. So therefore your C will be equals to PT power times time, how long you immerse it, divided by the mass of the water and the changes of temperature. Okay. Now, most of the time, what happened is in this kind of experiment, okay, the value of C you calculated, you have a theoretical value. What happened is this C value from the experiment you found will be actually greater. Okay, greater than the theory value. Okay, why is it greater? Because the increase. Why is it? Because the increase of the temperature is actually less. The increase of temperature is less than it is supposed to be. When this is less, because the others remain as constant. Because this is, if it were to be less, therefore your C will goes up. So your your experimental value will be greater than the theoretical value. Say if it were to be water, so it turns out to be maybe the value will be maybe 4,600 or 4,800 more. About maybe the water is 4,200. But it turns out to be 4,800. So this is normal, so don't fake your experimental value. Why is that so? Why? You need to ask. Why? First, because there's a heat loss. Where is it? Why is it heat loss? Where? I thought you have felt cloth, you have polystyrene sheets. The beaker. Okay? The beaker absorb the heat. Maybe the previous person made an experiment. It's very hot, but then you thought it's hot, not good. What happened is you wash it, make it cold at room temperature. So what happened? The heat supplied by the electric heater is not only used to heat up the water, but at the same time used to heat up the beaker. So this is where the heat is lost. The beaker absorbs the heat, partial of the heat. Okay. So this is one of the examples for the first law of thermodynamics and in the conservation of energy that normally comes out in experiment. Okay, I mean in a question form to let you know what's the time, the mass, the c and theta. Find out what's the power. Okay, P is power. Power. Okay, as in watt. Okay, so this is how it comes out. Then another example would be you mix two water. Okay, hot and cold water, milk and coffee. You need to have warm drink. How to do that? Okay, so the concept here would be this big cup, big beaker. Okay, you have two. One is the hot one, another is a cold one. Okay, maybe I use red if it were to be hot. Okay, and blue is cold. Say the initial temperature. Okay, mass for the cold in gram or gram, okay. Mass for the hot water. You mix them and you need to find out what is the T final. Now of course if it were to be hot, then you need to know what's the temperature here. This one is, they let you know what's the temperature, hot temperature. You know the temperature. You must know the temperature. I mean, it's denote, okay? Cold temperature. You know the temperature, you know the mass for the both cup. You need to find out what's the final temperature. Well, it will sound very complicated. It will sound very, very hard. But let me tell you, you could be wrong. Why is that so? Now this one here is very much on first law of thermodynamics. Energy transfer from where? From the hot to the cold. Meaning the hot water lose heat, lose energy, and the amount of energy lose, or the amount of energy lost, will be gained by the cold water. Yeah, it's logic. Okay, it's logic. You have lost. Where is it lost? Where will it gone? Gone to the cold water. So how? General equation, simple. Now, the hot water, M, hot water, C, theta. So it's the Q, hot, of loss, is equals to, it will be gained by the cold, isn't it? So what's the energy, or the energy loss by the hot? That will be the temperature final minus, hot and T final, isn't it? And therefore it will be gained by the mass of the cold water, except the heat of the cold. They are the same liquid, so it doesn't need to have C and H. It doesn't really matter because C should be the same. But then here, the final temperature should be higher, isn't it? Because it's cold, right? Initially. So, minus theta C. This is what you need to know. That's all it is. The sequence is important because otherwise you get a negative value. Okay? The sequence is important. So here, why is it TH in the front, TF at back? Because here is the hot water. Final temperature should be lower. So therefore you get a positive number. It's not the case, but in terms of explanation, is this is the energy loss by the hot water. Over here, this is energy gain, because if you were to gain, therefore the final temperature should be higher than your initial energy. That's why they are in an initial temperature. So therefore the final is at the front, the cold temperature at the back. So it means cold water gain energy. Okay, so simple. All you do, you put in all the number, rearrange them, and solve for T. can be done easily. Okay, so the rest of it, I mean, is very much based on this equation. Say, for example, kinetic to heat. Something moving very fast suddenly give it to a stop. Frictional force. Temperature increased by how much? So half mv squared. How fast is it traveling? And then what's the temperature increase? Okay, normally this is how. The same is true mgh, upstream, downstream. How far up, upstream, mgh, h in meter. M is in kg, h in meter. M is in kg, c is a constant. Theta is a change of temperature. So this is basically how you want to make use of the first law of thermodynamics. And from your textbook reference, you may go through some more experiment. Specific heat capacity of a solid, how you do it if it were to be solid. Okay, the same is true with water, but the setup will be a little bit different. That's why I would advise you to look at your reference, look for arrangement of apparatus. Pay attention to arrangement of apparatus. With that diagram set in your mind, you'll be able to write. All you need to do is to understand each and every part of it. Okay. Then the application. Okay. So next we'll go to application. How am I going to make use of it? What are the application for specific heat capacity? I mean, specific heat capacity. Specific heat capacity. Okay, how am I going to make use of it? So where you will find it, I think you need to read also. It came out in the SPM. Okay. Coolant. Look for coolant. Maybe from online. If you're watching YouTube, then maybe you look for this kind of guide online. Coolant in car engine. How does it work? Or you may read through the answer sheet in SPM. Okay. Then a household apparatus. Why some pot and pans? They are so expensive, but then the other is so affordable because of the material used. It has got very low specific heat capacity, so therefore the temperature increases very fast. In this is the trick. You need to choose low specific heat capacity so that the temperature increases fast. High is low, low is fast. Okay. Then another example. I'm going to show you. You need to read on this too. Coolant, car engine, household apparatus. I don't normally give everything in the video, otherwise you do not study. Okay, there's no shortcut. You need to read your reference. All my video is meant to help you out, so that you have some. Make sure, so to make sure you are on the same track, on the right track. Okay. Okay. Another example would be, I think I'm going to go through it because it's rather hard to understand. I'm sure you can make do with the car engine because it came out already. Well, it will be sea breeze. The phenomenon of sea breeze and land breeze. So, sea breeze, breeze mean wind. Okay, sea wind. Wind breeze. So what I would do now would be okay, sea breeze. Alright, this is a sand, and then you have water, sea water. Okay, water. And then in the noon you have a sun. So that is so hot. So what happened to the sea? This is a sea water, and this is a sand and your land. Okay. In daytime, obviously this is daytime. So between the sand is actually silicate. sand is silicon oxide. So seawater is a little bit salty, is H2O, basically H2O. So what happened in daytime? What happened? It's very hot, isn't it? The amount of energy to the sand and the amount of energy to the sea, they are the same. Okay? You can't say the amount of energy is different. The amount of energy Q is the same to the sea, to the sand, is the same. The heat is being absorbed, definitely, for sure. Now it's on the specific heat capacity. What happened to specific heat capacity to the sea is 4,200. It's definitely greater than the specific heat capacity for the sand. Maybe sand is about 800 joule in order to increase 1 kg per degree. Example is an example. It's not necessarily right. Maybe it's wrong. So say for example, okay, this is 800. You need 800 joule per kg per degree C. Whereas water maybe 420 joule per kg per degree C. For the same amount of heat, which temperature will increase higher or faster? Definitely would be your sand, isn't it? Sand, isn't it? 800 joule is already 1 degree. You give 800 joule per kg, 800 joule, you get 1 degree. Whereas for the sea, you need 4,200 joule in order to increase each kg per 1 degree. So definitely, the sand will increase warmer, isn't it? The land will be warmer than the sea. Definitely, for sure, isn't it? Because of this 2 value. If not 2 value, specific heat capacity of sea is greater than the sand. So therefore, the temperature increase faster in the land, inland. Temperature is higher in the land. So what happened to the temperature near the surface of the sand is higher? What happened? Hot air rises, because when it's very hot, what happened? It vibrates very fast, isn't it? The kinetic energy very high. So when the kinetic energy is very high, then they are further apart. So when we're further apart, then the density is mass per unit volume, isn't it? So the density of air decreases, correct or not? Near the surface. It decreases, what happens? It floats up. So therefore, you have a vacuum. Cold air, cooler air from the sea move towards the sand. That's why you have this sea breeze. Okay, so there are a few points here. I hope you will be able to get it. The same is true for land breeze. Okay, same place, same water. At night time, sea, and this is my sand, which is my land. At night time, so this is your moon, half moon. So what happened? At night time, what happened? It's a continual process, isn't it? At night time. This is night time. Night time. What happened? Come on. So any heat given? No, isn't it? So therefore, what happened? The heat is lost. Okay, heat is lost. At that time, heat is lost. Again, the C for the C is always more than the C for sand. It's always the same. It is a constant. That's why you call it constant. It won't change in either cases. It is a constant. So heat is lost. So who will lose faster? Who will cool faster? So every 800 joule increase. So meaning if every 800 joule of energy loss, temperature drop by 1 degree. So definitely the land, correct or not? So therefore the land cools faster because the specific heat capacity is lower. So it will become cold faster than the sea. Okay, so what happened? So the sea is warmer now. Sea is warmer. It's warmer than the land. Warmer. Okay. So what happened? Warmer. It's very hot. The density decrease, isn't it? So this is warmer. The density reduce. Rho density decrease. So it will goes up. Hot air rises, cold air sink. So what happened? The cold air from the land will go fill the vacuum created near the surface of the sea and therefore forms the land breeze. Cool air from the land move towards the sea. This is in fact the cool air, the cooler air, the cold air moves from land to the sea. That's where you have sea. That's how you get land breeze. Land wind. Okay? Land give wind. Land wind. Land give wind. Sea breeze. Sea give wind. Sea breeze. Okay? So I hope this video helps you with Form 4, Chapter 4 of Heat Part 2, Specific Heat Capacity. You need to really read on the application, understand it through the diagram, follow the flow of heat flow or water flow, and it helps you to understand it better. Okay, because coming up next video, that will be solely on specific of latent heat. Specific latent heat, you have a cooling curve and heating curve in our next video. So with that, I hope you share this video. If it's good, share this video with friends. If it helps you, press the thumbs up button. Follow me through the YouTube channel. Stay tuned for my next video. Thank you.